Hey folks, thanks for joining today. Today's video is the first in a series we're planning to make about large language models and their role in science. LLMs have been a huge focus in the last few years, and there have been some pretty impressive claims about their capabilities, particularly in regards to scientists and being at PhD level and being able to do research and that sort of thing.
This is the smartest AI in the world. Like Grok 4 is postgraduate, like PhD level in everything. Better than PhD, but like most PhDs would fail. With respect to academic questions, Grok 4 is better than PhD level in every subject, no exceptions.
But with GPT-5, now it's like talking to an expert, a legitimate PhD level expert in anything, any area you need, on demand, that can help you with whatever your goals are.
In my own experience with LLMs on a day-to-day basis, while they are undeniably useful, I think there's a bit of a disconnect between what people are saying about LLMs,
Every subject, no exceptions,
and what they can actually do. And I think some of that stems from possibly misunderstanding what it is we do as scientists. So the idea for this is pretty simple. I'm going to try and throw the kinds of problems and work that I do at an LLM and see what it can do. I think I'm in a pretty decent position to test this kind of thing, as I am a few weeks away from defending my PhD in astrophysics. So my level of work should be a good match based on some of the claims. Also, I have a full PhD's worth of expertise in the areas I studied, so I can judge the output pretty fairly, I think. I've authored, co-authored, and refereed papers in a variety of journals, including AppJ, AppJL, and Nature, so I'll be evaluating through that sort of lens, basically how I would evaluate fellow scientists and how I would expect my own work to be evaluated. I'm also really interested in this myself. If some of these claims are accurate, this could really be great for the field of science and my own research as well. So what I've done today is I'm going to start off easy and try to have ChatGPT solve a problem that I worked on as an undergrad. I wrote this paper in 2019. It was my first scientific paper and sort of the first project that I owned end to end. So we were studying this feature of black holes called their shadows, which is this critical boundary interior to which light can't really orbit, and so it can't or get out. It's not quite the event horizon, it's a little bit just outside. And this area has a lot of interest because, as we've discussed in past videos, David and I were both in the team that made the first image of a black hole shadow, so understanding its properties and how we can use it to make inferences about the black hole is really important. There's also really cool work in how we can test general relativity and probe theories beyond GR using this shape, so it's an area I really enjoy working in to this day. So anyway, in this paper, we made this pretty cool discovery about the black hole shape. The black hole shadow is generated by this fairly complex sequence of equations, which you don't need to worry about, but they can be difficult to work with, so there's been a lot of working trying to find approximations that can yield insights. You can do a series expansion of this to find an approximate shape, but that only works well in fairly narrow regimes around where you did the expansion, or you can find a shape that already looks similar, but that doesn't always tell you interesting things about the black hole shadow itself. Yeah, unless it matches exactly, you could be kind of just fooling yourself into thinking it's superficially similar. So we were investigating approximations using simple polar curves like circles and ellipses, and we found the shape called the Lamason, and it matches really well. So this is a comparison of the true black hole shadow versus the best fitting Lamason there. And as you increase the spin, the black hole shadow kind of slides to the right and flattens on one side, and it turns out the Lamason does that as well, just by changing one parameter, which is really interesting. The Lamason has two parameters, the overall size, lambda1, and then the asymmetry, lambda2, and that lines up really well with the black hole spin inclination. Even though they're not a one-to-one mapping, it's sort of a well-constrained problem. And then, so we did this whole analysis investigating the properties of the shape and discovered something genuinely new, which is that it turns out this shape is not just a good approximation, it's actually exact at both low and high spin. Low spin is trivial because it's a circle, but high spin, it turns out the black hole shadow is exactly a Lamason with these like minor modifications to make it more apparent, but the overall shape is exactly a modification. That's really remarkable because it turns out we were able to do all sorts of useful stuff with that. So what I'm curious to see is if ChatGPT, given all the same info, can do this level of analysis and come to the same conclusion and sort of make this discovery as well. It's fairly straightforward, and I think the easiest of the tests that I have planned. I'm going to ask it to not use anything past 2019, as I found out that when I was testing it, it found my paper and then plagiarized it a little bit, which, you know, it kind of defeats the purpose of testing to see if it can figure this out if it finds my paper and already knows about the discovery. So instead, it'll have all the info I did at the time, plus all the knowledge of mankind, apparently, up to 2019, right? Because whatever's in its training data set. So it should be in a much better position. So I'm going to ask it to do an analysis of polar curve approximations for the black hole shadow like we did. So we investigated ellipses and Lamasons and this a new shape that we found, and also we did this comparison to circles as well. So, we did quite a thorough analysis of polar approximations here. And then I'll give it a hint that it should be interested in exact representations. So I'll kind of nudge it to say, like, you should be looking for potentially something interesting along the exact representations. And then I will ask it to write a paper suitable for AppJ, which I think it should be able to do because it has all these AppJ papers in its training data set. So I think it should be able to handle that. I'll then evaluate it on the analysis, and then separately whether or not it made the discovery or how close it got. And then I'll evaluate the paper itself as if it was submitted to AppJ and I was a peer reviewer. So this is the prompt that I used, and here we go. So it took ChatGPT about 25 minutes to do the analysis and write the paper, which I'm going to download right there. And I've skimmed it already just to see what it put out and take a couple notes, but I'm going to go through it carefully with you pretty much for the first time. So we'll kind of get to experience it together. So let's get started. So this is the paper. It titled it, "How Well Can a Black Hole Shadow Be Approximated by Simple Polar Curves? A Curve Geometry Study with AppJ Style Analysis." A little literal, but I won't, I know that's just how the LLMs kind of roll, so that's fine. Okay, so, looking through it, it chose a circle, ellipse, Elemason. Okay, so I didn't tell it explicitly to choose Elemason, I think, so that's cool. And then these Fourier modes. Okay, so that's a little less cool. I think, the Elemason is just a n=1 Fourier mode, effectively. It's just, and I think, there was another paper that came out around the time that mine did, that broke into Fourier and maybe Legendre polynomials. So I think that might be basing it something similar to that. So I have no idea. I'm not sure how much of this was original. And for the Lemason, I know there's a 2002 paper by De Vries that looked at the Lemason as well. Not as much, anywhere near as much detail as our paper, but still, it's out there that the Lemason is sort of similar to the black hole shadow. So not clear on originality yet. Looking through the analysis, the actual equations, I mean, they look correct. This is something that's kind of interesting. So it didn't exactly, it sampled the black hole shadow onto a radial function. It claims a uniform angular grid. So I assume it's doing some interpolation, but it doesn't provide the details of the interpolation. And I don't see anything mentioned in the residual formula, but that's something that we had to be kind of careful about. Basically, when you take the Boyer-Lindquist coordinates and you produce this sort of set of radii, they don't correspond to nice even angles on the sky. And so your fits can be biased because there's more points near the top and bottom in the shadow than on the sides. And so we handled this in our paper by minimizing this quantity, which was a residual that was weighted by arc length. So that way, if there were more densely stamped points in a particular area, it wouldn't overweight that. It doesn't look like it did that. It's possible to interpolate it, but this is the kind of thing where it needs to provide those details so that other scientists can reproduce the work. So this makes me a little bit concerned because looking at this, I don't immediately know how accurate the fits are going to be. I see it's got the formulas right. Yeah, these are just regular. You can see that it's interpreting the Lemason as kind of a special case of the Fourier modes there. So that's interesting. These are the fits. Not super useful pictures because it's really hard to distinguish the different shapes, but it's good that it has this kind of figure. It's very similar to sort of what we had as well. But you can see that we went through a lot of effort to make sure you could easily distinguish the two shapes, especially here where we're trying to show the construction of the Lemason that exactly matches the black hole shadow. So, I would definitely have feedback for this if this was a student and I was advising them on this. Looking at the table down here, this is interesting, but so this is claiming the ellipse has a 0.02% median RMS. This is something that's not, I understand why it's saying this, and this is something that maybe you need human intuition for, but I was hoping the AI would realize this. But if you look at, for example, we have this nice plot showing the different black hole spins. If you look there, aside from very high edge-on inclination and very high spin, the black hole shadow is mostly circular. And in this case, we're very interested in how well the shadow can sort of the approximate formula can represent the shadow in this extreme regime. Like, I'm very interested in that personally. But that table of values is just taking the average sort of RMS, when I would have been curious to see how it varies with spin specifically. And we do have these plots down here, which I'm going to get to in a second, but it would have been nice to have something that's like really clear, something along the lines of this, where you have the RMS deviation. You can see it at a couple of inclinations for all spin, because that's where you get this really interesting, this interesting dip that occurs in the RMS deviation, where the Lemason, this is for a Lemason, it sort of gets a little bit better. It's almost monotonically getting worse and worse until max spin, but then it gets better. And for the convex hull Lemason, you can see that it dips and touches this point. And we did a bunch of interesting analysis on that, and there's a very beautiful geometric reason for it. But also you can see that it craters in the highest inclination here as the shape becomes accurate, as the shape becomes exact. So it didn't do any of that, basically. It just kind of averaged everything together, and it really misses that. And looking at the heat maps, I like the heat maps in principle, but they make the ellipse kind of look as good as the Lemason, which is, we know that's not correct from our paper. The ellipse tends to do worse than the Lemason most of the time. Maybe at higher spin, there's like a little bit of a difference, but so I'm a little surprised by this. I guess they're kind of close, but at low spin especially, it's interesting. And this black set of pixels at 0 spin is because there's no, it's just a circle, so it's exact, which is good that it caught that, but it would, I'm not seeing any exactness in the special case of the Lemason at the max spin, so it didn't catch that. And I'm also not, it's a little bit hard to tell, but I'm not seeing that it caught this interesting, maybe this hump over here is like this dip in the RMS deviation. Yeah, I'm not. My point is, in our plot, you can really clearly see that there's this dip, and it's really hard to see that from here. So I'm not. I would want. It missed it, which is a little sad. Looking at the conclusions, it's just a very bare bones summary, super bare bones actually. Definitely not. I'm going to mention this later, but that's not very good. But it doesn't mention anything about the interesting stuff that I wanted to see, which is a little disappointing. Okay, so that's on the analysis. I would say the analysis is pretty good overall. It has the fits, it has the formulas, it ran them, it made plots showing their similarities, it showed the RMS residuals, which is good in the table, and then it shows the residual as a function of angle, which is also good. Very interesting that there's these extra modes. The figures could use some work, but I think overall the analysis is fairly solid. Okay, so now looking at the discovery, from the discovery perspective, I would say this is a total failure. It missed that the Lemason in this special case is exact. This was our big discovery for this paper, and that's like the most interesting thing. This allowed us to do a bunch of other stuff. It didn't seem to catch that the Lemason has this interesting flattening, and I think it's because it roped in the Lemason with these other Fourier modes that are going to be easier to describe that kind of shape. But it's very interesting that the Lemason with the same number of parameters as the black hole shadow can describe the shape extremely well with the bulk properties that we're expecting. That suggests interesting things about the Kerr geometry that leads to this this boundary. But it didn't really catch that at all, that's disappointing. That's the kind of thing that I would hope it would catch. I would want to be able to see that. I would want to use LLMs to discover exactly this kind of thing, these interesting relationships. Now, I do see that it did capture this A sine I relationship. This is a pretty well-known angle, observer angle phenomena. So it's nice that it had it in there, but I don't think I doubt it's original because this has been known for a very long time. I'm also, like I said before in the analysis, it's a very uncreative representation of the parameter variation, which misses a lot of what makes it interesting. And a lot of them, when we're doing this kind of analysis, something we like to do is come up with creative ways to show the parameter space. So here we're showing how the different values of lambda 1 and lambda 2 change with spin at 4 different inclinations. But over here, we're mapping lambda 1 and the space of lambda 1 and lambda 2 and drawing contours of spin and inclination. And this is really, really powerful because it tells you something really interesting. So if you have a black hole shadow and you cannot set a constraint on the size, which means you don't know the mass to distance ratio very well, and all you have is the asymmetry, there's a limit to how good of a job you can do estimating the spin. You basically just say, I don't know what lambda 1 is, so if I measure lambda 2 perfectly, I can draw a line straight up through here, and that tells me all the possible spins that I could constrain further if I measure lambda 1 better, but if I can't, then I'm out of luck. So this is a really interesting thing, because even though the black hole shadow is not technically degenerate for any combination of spin and inclination, meaning there's no two combinations of spin and inclination that look exactly the same, even though it's not technically degenerate, there are practical degeneracies if you want to use this as a tool for measuring spin with interferometers. So this was really a very important part of our analysis, and it just totally missed it because of its very uncreative exploration of the parameters. It just put out, I think, what it thinks I wanted, and then did not do any actual reasoning or sort of interpretation, which is sad. Overall, I'd say it's really boring. Like, it missed the most exciting things. I have more thoughts on this, but I want to review the paper now from the paper writing perspective. So the abstract is good. It's a good, tight summary. I think this is where LLMs shine in general, is these sort of tight, concise summaries. The introduction is just way too light from a paper writing perspective. The literature review needs to be significantly more complete. You need to show you understand what has been done and where your own work fits in. And this would not even be good enough for a Wikipedia entry, never mind an AppJ paper. And maybe I'm too harsh on the literature review, but it's kind of been beaten into me that you need to have a really good understanding of what has already been done so that you can insert your own work into this landscape or this tapestry. And I would expect LLMs to be very good at this because they have absorbed all of humanity's collective knowledge. So I'm surprised that it cannot come up with a better summary that sort of has more specific results. So that's a little bit disappointing. And I mean, you can see from the references section, it's only like 7 references, which is like, this is just not enough. And 2 of them are the same, right? This is the first and second papers of the Sagittarius Star series. And I actually don't understand why it's citing that paper 2 of the Sagittarius Star series, because paper 2 should be, I think paper 2 was was just discussing the observation strategy or the calibration. Maybe that was paper 3. By the way, it's not discussing imaging or the theory. I would expect paper 5 maybe to be a more relevant citation. But I'm mixing up because I was also part of the Sagittarius Star results, and we had different numberings for those. But these are not the 2 papers I'd expect. Paper A makes sense because that's the abstract paper where it sort of summarizes everything. But the second paper I don't think would be really relevant for this. So I think there's more. I think there's more that should have been cited. But that's fine. I'll move on. The statements of the equations are a little bit weird. They're fine, but I think it's like a little bit weird to cite the 2009 paper. I need to go back and review Made It. Maybe this is just exactly how it's presented in Made It, and it shows that. I would have chosen the Bardeen representation or the Takahashi, but either way, this is not sort of what I was looking for here. It's unclear why it chose 221 shadows. Like, it chose 17 spins, 13 inclinations. Seems super arbitrary. No idea why it did that. Would have preferred, instead of evenly sampling the spins, more spins closer to max spin, because that's where all the interesting stuff happens. I'm a little surprised by this. The sort of terse, undescriptive bullet points here are really a big no-no. I'm a little unclear if because it's supposed to nominally trained on a lot of scientific papers, so I'm not sure where it picked up this style of writing where you're just writing these bullet points, because this is not what I would expect from an AppJ paper, so I'm not happy with that. There's very little information given about the procedure, so it'd be really hard for someone to reproduce this if they ran into problems. I like the discussion of limitations. So there's a section 5.2 on limitations. I like this discussion. The implications of seems to be that if we modeled EHT images directly, this would be applicable, and it is not. The EHT can't see the photon ring at all, and even if it could, it can't see the critical curve, which is more of a theoretical boundary than something you can really measure off the images, except in very specific scenarios. So these limitations are interesting and I mean, sort of accurate, but they're not. I don't know how useful this description is. And even if I may be misinterpreting what it said because it writes so tersely and so unclear, which is not great. Here are my overall thoughts. So, in summary, the analysis is pretty solid. It did a decent job crunching some of the numbers, and I was impressed that it could take the concept from idea to fit to execution and plot and report on the results. That's really cool. That's genuinely amazing. But I was pretty disappointed that it couldn't find any of the interesting nuggets that made this analysis worth publishing. This is exactly where I sort of hoped LLMs would be useful. They have access to all this information, but can't reason more than tiny basic steps, and I suspect this will be a limitation for a long time. Now, the writing also leaves a lot to be desired. It's nowhere near acceptable for technical writing. Jargon does not equal competence, and there is not enough detail, literature review, or communication to really even be marginally useful as written. Overall, if I were to grade it, would I'm going to talk about it from the perspective of a journal, but this feels more like something a high schooler would write. A very capable high schooler, like, they have an impressive ability to program and can work with simple equations that are given to them, sure. But this is not, I would not call this PhD level reasoning, in my opinion. And it's honestly not what I was expecting, given the emphasis on PhD level reasoning in everything, right, is what we're told, and beyond PhD stuff. I think that there's a serious misconception about what we do as scientists and researchers, but this experiment did help illuminate that for me. As a researcher, the fitting and plot making is a necessary medium for our scientific expression, but the actual thing that we're trying to do here is make discoveries, look at problems from new angles, and learn genuinely new things. Adding meaningful things to humanity's body of knowledge. Claims of PhD level reasoning seem to be confusing being able to do graduate level homework problems with the actual hard part of our jobs, which is finding truly new things. It's very easy to solve a homework problem when you have access to literally all knowledge, including possibly all those homework problem solutions in 1,000 different forms. The hard part about science is the stuff that's outside the structure and the problems. In this case, it was discovering that if you shift the black hole shadow slightly, it collapses exactly to this beautiful shape in one limit that serves as a useful proxy across all of the Kerr parameter space. There's no way for ChatGPT to probabilistically learn that from its training data, and it failed fairly dismally, missing it entirely. This is disappointing because this is exactly what we're hoping these tools will be able to do for us, which is discover things we can't using superhuman reasoning. And that's what the claims of beyond PhD ability evoke, but I'm just not seeing it yet from this. It can do some basic stuff, follow a couple of steps, but there was nothing here that suggested that if this discovery was not already in its training data, it could have discovered it on its own. Not without significant prodding by telling it like, oh, what happens if you do this or that? And while that's really useful, what it can do already, I'm very confused by this beyond PhD level reasoning claims. So I have a few more of these planned, so stay tuned. The next one is going to be about a supernova paper I wrote, so subscribe if you like exploding stars. And I also want to shout out the YouTube channel Easy Writers, who did a similar sort of test to this, but in mathematics, and that's what inspired this sort of series of videos. So go check out his videos, they're great, and thanks so much for watching.